All right, good morning. So I will continue today with the second lecture, and I wanted to try and make this connection between a theory of gravity and theories that don't contain gravity. So I've written many body physics. But in the most general context, it's actually something like quantum field theory that should be here. And in particular, the most famous examples are ones that involve so-called conformal field theories. But that's not an aspect that I want to emphasize particularly here. So, however, I did want to still first give some intuitive arguments why we should think of black holes as chaotic systems, actually. However, to make those connections more precise and to really talk about precise notions of many-body chaos that I believe most of you are really experts in, we will need this mapping, and that will then occupy the last lecture to make some of these statements about in what sense are chaotic more precise. But at the level even of thinking about semi-classical gravity, which I introduced last time, there is actually a way of arguing why we should assume that black holes are classical systems, are chaotic systems. So let's see, black holes are chaotic, and an intuitive reason one might give, so that is not actually a very rigorous reason, but those Einstein equations that I talked about, the Einstein equations, they are nonlinear PDE, and actually generically such things you expect to have chaotic behavior. Of course, you could be in the case of having a nonlinear integrable system, but I will now tell you that actually at the classical or semi-classical level things thermalize, and therefore it is a natural it's a natural expectation that that those things actually are, have thermalizing dynamical behavior and therefore show notions of chaotic behavior. So let me tell you this argument for why black holes can be thought of as thermal systems. And it actually probably also will shed some light on the statements I made about Bekenstein-Hawking entropy and so on and so forth. So more intuition, let's say. So firstly, I want to say that, again, the black hole finds a thermodynamic ensemble. And how does this work? Well, I want to argue for you that matter that moves in the presence of a black hole, if you study its correlation functions, they will satisfy something like the KMS conditions. So they are periodic in imaginary time. But in order to argue this, there's actually a very slick and geometric argument in favor of this, which I would like to tell you about. So let's say that, so first of all, we want to say something about imaginary time. Right, because actually finally, okay, because we want to say something like about e to the minus beta h, where beta is, of course, just the inverse temperature, but it is evolution in imaginary time. So now we have something like the actual way of thinking about the black hole. The best way to think about it, or one good way to think about it, is to write down the line element. So for the simplest one, the Schwarzschild black hole, that is given by 1 minus Schwarzschild radius over the radial coordinate dt squared. So this is Lorentzian time plus the same factor r Schwarzschild over radius inverse dr squared plus, and there could be other directions. What I mean by this is, if you have a 4-dimensional black hole, you will have 4 coordinates, so there will be 2 angles that form a sphere, but we could also think of this as being a high dimensional solution and so on. But all the interesting stuff happens in this radial and time two-dimensional plane, T and R. And so if we want to go from this, right, what we have is something like IT. So of course, you want to think of d by dt as being the generator of time translations. So this is something like the Hamiltonian. But if you want to go in the imaginary time direction, then you need to go to d by dt. Okay. And so that motivates you to consider this solution, which is the physical solution of Schwarzschild. It should write this nevertheless. So what I wrote here is the Schwarzschild line element. So the ds squared above is the line element of Schwarzschild black hole. And RS, I think it's just twice the mass, is known as the Schwarzschild radius. Schwarzschild radius. And it is the location of the horizon. And moreover, as I also already said in my sketch last time, at r is equal to 0, this metric is singular. So invariant curvatures actually diverge to infinity at r is equal to 0. They do not diverge at r equals to rs. You see that the metric becomes degenerate because, you know, dt, the factor here goes to 0. So there is a huge amount of time dilatation, this relativistic effect. And this guy diverges, but that turns out to be famously just a coordinate singularity. And we could choose better coordinates and we could make it non-singular at the horizon, but we could never make it non-singular at the origin, because this is where actually gauge invariant physical quantities diverge, such as curvature scalars squared and so on. Okay, but now comes something that maybe is a little bit confusing, because I've emphasized to you that here the horizon is not singular. Okay, maybe I should say horizon is not a physical singularity. Okay, because we can choose coordinates that nothing happens to physical gauge invariant quantities that would be in any way disquieting. However, now the idea is to go to imaginary time and to rewrite this thing as a complexified solution such that we can choose a direction that is imaginary time. So what we do is we Wick rotate, if you want, and we get a solution which is ds squared is now plus 1 minus rs over r times d tau squared. Okay, tau is equal to it. Tau is equal to it. So that's it's a trivial manipulation. It just puts a plus here. Okay, and nothing happens to the radial direction. Inverse the r squared plus angles theta phi maybe. So now, however, this metric has a problem. So this metric is actually the metric of a cone. So it's actually a metric that has a direction tau which goes around here, and it has still the radial direction which goes. Actually, if you want, it's a disk where I have an origin, and I should think of tau now as the direction, the angular direction. And the problem is that this point here, this point is actually singular. Point where the Lorentzian metric would have had its horizon. The point r is equal to rs. So now the only way to save the situation, to think of this as a regular metric, is to say that we know what we can do if you have an angular coordinate on a disk. If the angular coordinate is periodic with period 2 pi, then I just have spherical polar coordinates parameterizing a completely non-singular plane. Okay, so this singularity is avoided only. So yeah, singularity is avoided only if tau is actually periodic, and it turns out that okay, you have to put some factors here. Tau has to be identified with tau plus something that I call beta, where beta is 1 over the Hawking temperature, which we determined last time was 1 over 8 pi m, which is 1 over 4 pi times the Schwarzschild radius. Okay, so I repeat the argument one more time. If you look at the point r is equal to rs, but now in this complexified version of the black hole, because we want to think about imaginary time evolution to get to something like e to the minus beta h, then this metric suddenly turns out to be singular at the horizon, which we don't want. And so the singularity can be avoided, however, if tau is a periodic variable with a particular identification. And this identification turns out to be precisely the inverse Hawking temperature. So if you want, to some extent, this is a derivation of the Hawking temperature of a black hole, but I think it's very abstract and almost too slick to really be believable. One could put more meat to this and make it more believable, but that would take me a good part of my remaining time. But what I want to say is that we should think, therefore, now of the Euclidean version of black hole as being this geometry, which is a disk, which happens to have a conical singularity unless the imaginary time is identified with 1 over the Hawking temperature. Means, however, that now time itself, really the Euclidean time itself for every observer is periodically identified. So that means that all correlation functions of, let's say, matter in the presence of the black hole are periodic. Tau should be identified with tau plus beta, or if you want, of course, t is t plus I beta. So you can also translate time into in the Euclidean direction. And so therefore, you can actually show that correlation functions. So therefore, if you look at correlation functions of quantum fields in the background of the black hole, they actually automatically give you the answer that you will get from inserting e to the minus beta times the Hamiltonian into the correlation function, where beta is 1 over the Hawking temperature. Okay, and in that sense, that's what classical gravity people mean when they say a black hole defines a thermodynamic ensemble. So it's as if like every observer around the black hole experienced the thermal average of whatever fields they measure. And the thermal average really comes from the fact that the black hole forces this very particular periodicity of imaginary time. Now, I should say that there are also much more complicated, but maybe more convincing arguments, which are actually originally Hawking's arguments, which show via Lorentzian calculations that an observer who is moving in the background of a black hole perceives thermal radiation at this temperature. I think these are ultimately more convincing, but they would take a whole set of lectures to explain. Yes, Jorge. Not to my knowledge. And you see, the thing is really, again, so some similar to the question I got last time, is what other system is there that really defines what time is? I mean, the thing here is that this thing really tells you that Euclidean time has to be periodic. And when you move in that arena, which is given by the black hole metric, this is the time that you experience. Of course, you experience it somewhat indirectly because you experience it through Euclidean evolution. Not to my knowledge. I would not know how to make such an argument. No, this is there is no such definition actually. So in some sense, different observers will perceive slightly different physics. So this is a Schwarzschild observer who perceives this time coordinate. But of course, if you wanted, for example, to go to a different time coordinate, there is actually this, I don't know what it's called, maybe Tolman or something like that. There's Tolman's law, for example, that the local temperature is actually different. Yeah, but I'm working specifically with respect to a Schwarzschild observer, and this is the time that they will, this is the temperature that they will experience. Yeah. Oh, well, I don't want to do the calculation now, but what you need to do is, no, it's not that difficult, but I can just tell you what to do. You literally expand around r is equal to rs to linear order, and then you get something like d tau squared with some coefficient plus the deviation from the horizon squared times, sorry, you get dr squared plus the deviation squared times dt squared, and that's of the same form as just spherical polar coordinates, but there are some factors which depend on m. But then you transform it into the actual form of spherical polars, and then you say tau rescaled by those factors is just phi. Phi needs to be 2 pi periodic, and then translating back to tau, you get this periodicity. And so if you don't make it 2 pi periodic, you get the dr squared plus r squared d phi squared, but you've cut out this piece of the cake, and you of course know when you glue that, you get the point here. Yeah. That's exactly right. That's exactly right. So a better way of going about this with more time would have been to again write down this path integral that I wrote down, and to say, okay, with a cutoff we can make sense of it. Now let's calculate it. Then you do like, you know, there's gauge invariance, so you need to do Faddeev Popov and so on and so forth. But you find that there is actually a well-defined path integral, and then in that path integral, however, you have this periodicity. So everything that you insert, all the correlation functions will inherit this periodicity. So that's actually, that would be the long argument, which is slightly more convincing than this. The really convincing argument is the Lorentzian arguments that were given by people like Hawking, Unruh, also Thibaut d'Amour, and so on. Okay, so now that is sort of one way of saying that a black hole is a thermal ensemble or acts like a thermal ensemble. Now, thermalization. Now, the point is black holes actually form. So black holes form from generic initial data, meaning that you don't have to fine-tune the initial data. So the idea, or what people usually say, is that let's start at some time. So this is again Lorentzian. Okay, so time goes like this, and you start with some initial time slice like t is equal to t0, and you have some distribution of matter, I'm not sure I can fit this now. I think I need to start earlier. So T0, and you have some matter, but this matter under its own gravity, it will collapse in on itself. So this is now like this cloud of matter, which becomes more and more compact. And in fact, so this is the content of Penrose and Hawking's theorems, is that generic will form a singularity, and in doing so, it is believed that always, at some point, a horizon will form around this singularity. So let me label things again. So this is the singularity. This is the black hole horizon. This is some matter cloud, and here it collapses. So this is like a star that's collapsing, if you want, star collapse after it. And so the point is that eventually you get one of this weird object, which is a horizon, but it will be a very messy thing. It will be inhomogeneous and so on. But then through further evolution, eventually settle down, and it will approach one of these equilibrium solutions. In fact, it will generically approach something like Schwarzschild, perhaps with some rotation, which would be the so-called cursor. But that means that you can start with some matter, which you should think of some generic initial state, which is not in a thermal ensemble, but generically, gravitational evolution will produce this thermal ensemble for you. So this is actually a process of thermalization. And what I want to say is that actually a lot of the research that we have done, and that also has led to, I think, other people have had some great insights on how to think of this as a thermalization process. It has precisely been appreciated that we can learn a lot about what happens in gravity by thinking of this in a quantum system thermalization way. But in order to do this in a useful way, that's when I need to go to this gravity and many-body physics connection. Because what I told you here, this is stuff that really does happen in our universe. However, I've been working at a sort of generic level. So this could be a black hole in any number of dimensions, and it could be a black hole in any kind of asymptotic geometry. I will actually go to asymptotic geometries in a minute, so maybe that comment will become clearer. But from a theoretical point of view, we can make this extremely precise, and we can make a very close connection between this process of thermalization and things like, for example, what Laura is talking about, like eigenstate thermalization, or even random matrix theory at very late phases of this evaporation, of this collapse. Let's not yet talk about evaporation. But for this, we need to go away from the real world for technical reasons that I shall illustrate. And we need to talk about black holes live in a somewhat more exotic space-time, different from the one that we live in, because this is where we have much more theoretical control, and we can make an explicit map between what's happening here and between the notions of many-body quantum chaos. Okay. The black hole horizon. No, we know that it leads to a singularity. That's a theorem. That is called Penrose's theorem. Now there is a conjecture, a mathematical conjecture, which is called the cosmic censorship conjecture, which says that solutions of these nonlinear partial differential equations, whenever they go singular, the singularity will be hidden by a horizon. This is not proven yet. If you prove that in the field of PDEs, it will be a big deal. There are two versions of this, but let's not go into it. One weak and one strong one. The weak one is actually much more subtle. Yes, black holes are somehow dissipative. And it's really confusing. That's right. That's right. Yes, but generic, the point is still that there exists in the space of all initial conditions endowed with the correct metric, there exists a measure non-zero set of initial data that goes to a black hole. I'm not saying that the measure is one. In fact, it's not. But it was believed, it was really believed until these theorems that it was measure zero, that only very special spherically symmetric solutions exist, which had this weird property that they were singular. But in fact, it happens under generic circumstances. And that's important. Okay. So now I want to go to this holographic duality. Basically, in order to make this connection more precise to the actual thermalization process, maybe something like eigenstate thermalization and so on. So I say maybe because it depends a little bit on how much time I have. But yeah, I'll decide what to mention tomorrow. Yeah, what was the trick again with the water that didn't work? Oh yes, that will be much better. Yes, yes, yes. Yeah. So now I want to go to this idea of holographic duality, or let's call it here many-body gravity duality. Okay, and so first of all, I want to clarify this statement I made about asymptopia. So a black hole is in some sense a local object, in some other sense it's actually not, but you just have space-time and it can be there somewhere like a star, it will be localized. And so the question is that if you go far away from the black hole, what does space-time look like? And there basically we have three options. So far away from our black hole, we find what people like to call asymptopia. So this is space-time that behaves as if there were no black hole, because we're so far away that the black hole doesn't anymore affect local physics. And now we're just asking sort of what options do Einstein's equations leave for the notion of empty space? And so there are actually three options. There is this famous cosmological concept which I wrote. So let's, we have our Einstein theory, and the most relevant operator is actually this cosmological constant lambda, and then there could be higher derivative corrections which come in because of this effective field theory thinking, but I didn't specify much. This is the determinant of the Lorentzian metric, and so lambda, you have three options. Lambda could be positive, in which case this asymptopia, the space far away, will look like what we call the Sitter space. And that's presumably the best approximation out of these three options to the universe that we actually live in. Then there is the case which I actually treated in equations, lambda is equal to 0, which is just Minkowski space. We also call it flat space. And then there's the option of lambda less than 0, which is called anti-de Sitter space. And the reason, of course, for the name is that de Sitter was an actual person. He thought about cosmology, and he realized that you could write down this solution of Einstein's equations that has positive curvature and constant curvature and corresponds to a lambda greater than 0 solution of Einstein's equations. And then subsequently, people considered the same solution or an analogous solution with negative constant curvature, and lambda is less than 0, and that's why they called it anti-de Sitter. And so reasons that I must say, personally also, I don't really understand. This holographic duality for the time being will only work if you choose the behavior far away from the object that you're interested in to be anti-de Sitter. So let me just say, maybe I will still write this as terminology. So these are the three maximally symmetric constant curvature solutions of Einstein's equations, where Einstein's equations I define to be the equations where we include the cosmological constant, possibly with value 0. And so these are like arguments in differential geometry, where you can actually classify the constant curvature solutions, and you find that there are only 3 which are sort of maximally symmetric. Maximally symmetric means that they have the biggest possible number of isometry directions, meaning directions that if you move in them, they don't change. So in Minkowski space, we're quite familiar with that. You have things like rotations. You also have Lorentz transformations. You have translations. And in anti-de Sitter space and de Sitter space, those geometric notions are slightly changed, but there is the same number of them. Okay, and so there is actually one very simple reason, well, not simple reason, but one thing that distinguishes anti-de Sitter from the other cases, which is one indication why there's something special here, is that, as I said, the set of symmetries of flat space corresponds to the Poincaré group. The set of symmetries of anti-de Sitter space actually corresponds to the conformal group. And so the notion of conformal symmetry here will be very helpful. But this is not the kind of discussion I want to get into. You're free to ask me, of course, also in private if you want more of these sort of more mathematical explanations, or let's say more detailed explanations. Yeah. Well, de Sitter has some kind of Euclidean version of conformal symmetry. In fact, there is a paper by Dirac from the 1930s in which he classifies the symmetries of de Sitter, and it's actually the first paper that classifies something like unitary representations of the conformal group. So I do want to say a little bit about ADS geometry, so elements of ADS geometry. I mean, the reason being that I appreciate that this is sort of a little bit of an exotic object for people who are not working on it, but I just want to point out that it isn't in fact all that exotic or all that complicated. There's a very simple way of defining what this is. The best way I know of defining what this is to actually write an algebraic equation that the solution of which is anti-de Sitter space. So this algebraic equation is the following. We take some coordinates capital X. So X, the coordinates will live in some auxiliary space, which happens to be B plus 2-dimensional, which has 2 time directions. That's weird, but it's just an auxiliary construction. The actual anti-de Sitter space only has 1 time direction, like it should. But now we write a hyperboloid in this space, which is the following equation. so minus x0 squared, that's one of the time directions. Then I have a bunch of spatial directions, which I add with positive coefficients. And then I have another time direction, which I label b plus 1 squared. And I say that this satisfies minus is equal to minus L squared for L real. If I swap, if I analytically continued this to IL, I would get the Sitter space. So so this is one equation among d plus 2 coordinates. If I solve it, I get d plus 1 coordinates. And so the solution will give coordinates on anti-de Sitter space with d plus 1 directions. D plus 1 is sort of some convention that we like to use. I think you will appreciate in a minute why we want to have one dimension more than d. But this, we can visualize it. Let's say if we just take the case where we have x0, x1, and x d plus 1. So this will become two-dimensional anti-de Sitter space, and two-dimensional anti-de Sitter here be the surface of this hyperboloid of revolution that is defined by this equation, which actually just happens to be, you draw these hyperbole, and then you have a circle direction. You will have a circle direction d plus 1 x0. Let's just write it. You have something like x0 squared plus x d plus 1 squared minus x1 squared is equal to L squared. So these directions here are a circle, and x0 with either x0 or xd plus 1 with x1 is a hyperboloid. So you get this hyperboloid of revolution. So it's some nice, simple algebraic surface, which just happens to be embedded in a weird space because it has two time directions. And then what you do is you take the flat metric. So nothing actually, just take Minkowski space of this weird signature. And you ask what metric does it induce on this hyperboloid of revolution. And that is exactly ADS 2 in this case, ADS 1 plus 1. So it's a very simple object. You can even draw it in low dimensions. I just drew it, okay? It's a constant negative curvature hypersurface that can be embedded in some Cartesian space, be it with a slightly weird signature. Okay, so those of you who are working in conformal field theory, they maybe actually know this construction because this is a super efficient way of thinking about conformal representations by first thinking about some weird Lorentz group in 2, d. I always say weird because we have one more time, and then inducing representations on ADS, and that gives you the full representation of the conformal group. It's called the embedding formalism. Okay, so here is anti-de Sitter space. But there is actually the way that most people represent anti-de Sitter space is slightly different, and that's because it will illustrate some aspect which will become very important. So let me also give you that other representation. So now suppose that we chose some coordinates, meaning we chose a particular way of solving that algebraic equation. There's more than one way of solving it, and each will just give you a different coordinate system, but on the same actual geometric object, which is anti-de Sitter. Are there questions about this, by the way? I should. Yes. Yeah, so that's one subtlety that I didn't want to go to. So the time here is indeed periodic, but what you call anti-de Sitter space, the physical space, is like the covering space of this, where you decompactify time. Other questions? Okay. So unlike flat space, ADS has a boundary. So the way that people represent this is they say, let's actually think of ADS now as a cylinder, a solid cylinder. Okay? And so there is the mantle of the cylinder, which is the boundary. Now this is this compactified Lorentzian time that goes up. And then there is a direction here, which I've drawn as a circle, but in general, it's something like S d minus 1. And then there's the direction that goes radially inwards. So this is the solid cylinder, and we refer to the inside as the bulk. And we refer to the mantle of the cylinder as the boundary. Okay, and so you can have excitations that live inside of this space, which go from the inside to the boundary and bounce off the boundary, for example. So you can actually reach this boundary with physical excitations. And this is drastically different from the way that Minkowski space behaves, the flat space. There, when you send something away, it just goes to infinity. You'll never see it again. It just goes away. Here, this space, and people therefore like to refer to it as gravity in a box. It's like you need to specify what happens on the boundary. You need to specify, for example, whether they're like Dirichlet or Neumann boundary conditions here. And depending on your choices, that will change the physical evolution of field. It's not immediately obvious to see why it has a boundary. The way we would do it, if we wanted to spend that time, is I would write down for you the global metric on anti-de Sitter space, and I would show that there exists what's called a conformal boundary. So you do need to, yeah, there are some maneuvers you need to do, but so that's also the reason that's not obvious from this hyperboloid, that it has a boundary is the problem that you have to define a conformal boundary. Yeah, but I don't really want to get into it now. But it is true that to define evolution of any excitation in anti-de Sitter space, you need to specify boundary conditions at this conformal boundary. That's important because you actually see things again that bounce off this conformal boundary. But it's a fair question. Yeah. So there is a sphere that you can see. The sphere is basically the sphere is going to be the sphere that is spanned by some subset of the spatial coordinates. And that sphere comes up here as every point here is multiplied by a sphere, but in the boundary, you see it as the actual sphere of the boundary. Yeah. So the easiest way of solving this kind of constraint is that everything that comes with a plus, you solve with angles like sines and cosines, and everything that comes with minus signs, you take you take hyperbolic functions like cinches and coshs, and then you get metrics, which is of the kind like almost looks like an n-dimensional sphere, but some of the directions have cinches and not sines. And those are the non-compact directions in which you can go off to the boundary. And the rest are the sphere directions, which are basically these rotational directions. We can go through this in detail if you want. So, but okay, so now this is what people like to call the ADS cylinder. And it is, yeah, it is a physically useful, but maybe less faithful graphical representation of what really is going on. Now, let's see, where can I go? So okay, so that is what I wanted to say about asymptopia. So there are these three different choices. Flat space or de Sitter are probably the ones that correspond more to the world that we live in. but anti-de Sitter has this nice property that I can actually describe the physics, gravitational physics of anti-de Sitter space using the so-called holographic duality. And this is where I want to go now. So I want to tell you a little bit where this comes from. So the holographic principle. So the good way of arguing for this, or well, I don't know if it's a good way, but one way that we've already seen is that we take note of the fact that the black hole entropy was extensive in the area of the horizon. Okay, and the point being that it's not volume of the black hole. Okay, so somehow, so the number of degrees of freedom that are associated to this, okay, are extensive with surface area in Planck units. And that is very much unlike ordinary matter, of course. And so what has happened, people have declared this as a general principle of theories of gravity. Why? The idea being that what you can do is you can spend all your time throwing matter into a region of space-time, ordinary matter, which has volume extensive entropy. But eventually, if you throw too much matter, it will collapse into a black hole, into a very dense object, which will form a horizon. And the horizon, again, will have this property. So somehow, the strong nature of gravity rearranges degrees of freedom in such a way that their entropy becomes area extensive and not volume extensive. And so since everything eventually, if it's dense enough, forms a black hole, then people were basically saying that a region of space-time, any region of space-time, should be described by a microscopic theory living on its boundary. Okay, so first of all, that's of course a very vague, very a grand statement. So I will go on to try and put some meat on this, but for the time being, I also wanted to point out this is why, of course, people like to call it the holographic principle, because it's precisely the point that you have a region, a volume, but in fact, all you can do in this volume can be encoded equivalently on a surface around it. And so this is the idea that the hologram is a two-dimensional thing, but it really actually has three-dimensional information. Like you can see different angles by looking at different ways at the hologram. And that's also in the end will be the reason why we always tack this one in the ADS, because the boundary of ADS d plus 1 is some d-dimensional manifold. Let me call it MD. And the precise realization of this holographic principle in the context of ADS space will be that there actually exists a microscopic theory that lives on the d-dimensional boundary of ADS d plus 1. And I can use this microscopic theory to define quantum gravity in ADS. Okay. And in fact, in recent years, we really have been able to make those things very precise, particularly in low dimensions, where we can write down what this microscopic theory is, and we can rather explicitly do calculations. And this is this famous SYK context, and I think I will talk about this more tomorrow. Okay, but for now, the point is that we should so holographic duality, or sometimes also called ADS CFT, is a realization that is actually mathematically calculable, the realization of this idea. So for many years, this sort of idea was around. People had, Toft had actually had conjectured it, and people like Susskind and Polyakov had been saying that this should somehow be true, motivated by various different ideas. I think the clearest sort of conceptual motivation is this observation of the horizon extensive nature of the black hole entropy. But in fact, in the late 90s, a precise realization of this was proposed, and that's the thing that people call ADS-CFT, because it in particular refers to the space-time region being ADS space, and it classifies the theories on the boundary as conformal field theories that are able to realize this idea. Okay, so let me give you some elements of how this ADS-CFT works. That will be the last thing I will have time to talk about today. And then tomorrow we'll go to, I think, actually, again, an arena that will be more familiar to you, where we focus on a particular realization where there is a many-body system whose Hamiltonian I can write down, and all of these things where I say you insert a source here and you differentiate there and so on, we can actually do it. Okay, but for the rest of the time today, I'm going to do this thing where I say I'm inserting a source here, and then you can differentiate, and this will happen. Okay. Now, questions? Yeah. Yeah. No. I mean, from this black hole argument, I mean, the horizon does actually form the boundary of what's inside. Okay, so in that sense, it's natural that it lives on the actual boundary of your system. But more abstractly, it's true that I don't think there needs to be a geometric connection like this. But all of the cases that I'm aware of have such a relationship. That's right. Yeah. Well, you don't even need to have things to fall inside. You can also just have no black hole, and you stuff more and more matter. Eventually, it will be inside its own Schwarzschild radius, will form a black hole, which will be extremely compact compared to the matter that it was before. And the entropy will be proportional to the surface area. But you should do the exercise once and look at how big actually is the entropy of a black hole, even though it's just proportional to its area, because the density of entropy is enormous. So they're still extremely highly entropic objects. Because eventually everything is able to form a black hole. Right. So, other questions? So, one would like to develop a formalism such that all of the degrees of freedom reside on the degree of the space-time region. And such a formalism takes the following form. So, yeah. So let's just write, like, again, schematically. Let's say there's a space-time region which has like a black hole inside of it. Okay, and I have sort of roughly surrounded it by surface, which I will think of as boundary. This is just drawing pictures. Better pictures would have been to immediately draw pictures of black holes in ADS and so on, but it doesn't make much of a difference right now. Now, the holography then if you want, is a mapping or a set of rules that maps observables between the bulk and the boundary. So let's say bulk and boundary. So for example, or not for example, actually generically, the thing that you want to calculate will be some correlation function. So you want to say something like, in my boundary theory. So let me specialize to this case, just notationally, where this is indeed ADSB plus 1, and this will be some d-dimensional CFT. Then you might want to calculate correlation functions of operators in the CFT. Those are the observables, most generic observables that you could think of. And they are, of course, just given by some generating function of sources for the operators. So this is the these are the objects of, for example, correlation functions here. Correlations. And the statement is that actually there is an object which is the gravitational partition function, very much like the one we would calculate, that depends on, well, that is an integral over the metric, and that might also contain other degrees of freedom which are associated to these operators. Okay. And the statement is that this is actually W of J omega, sorry, Jo, for this operator, where I give boundary conditions such that, so I do my path integral, so Z of G phi O actually is this path integral over all the degrees of freedom that I have, e to the minus the action of gravity with boundary conditions. And the boundary conditions are such that the field phi that is associated to this operator phi, as I go to the boundary, R goes to, let's call it R infinity, becomes exactly the source Jo as a mathematical function. So we can draw this in pictures, which is a little bit better, is that have some bulk in general quantum field, which extends to the boundary. So this is my phi, which depends on the radial direction and all the directions around the boundary. And at the boundary, it takes the role of this source Jo of x mu. And if I'm able to calculate this path integral, which is of course a tall order, okay, then what I've actually done is I've secretly calculated the generating function of all CFT correlation functions on the boundary. Yeah. J is not necessarily infinitesimal, but if you want, for example, the 2-point function, the first derivative is sufficient. You can just do linear response, and then you might as well take it infinitesimal. But you can calculate in the presence of a finite source. No, you can take both. You can take both. So that was going to be my next comment. So in general, this is what people like to call the holographic dictionary, or at least the most important entry, and they call it the G K P W formula. Sorry, this is I don't know why I'm saying this in response to your question, but I will. There's Giddings, Klebanov, Polyakov, and Witten who first wrote down this formula here, but actually, in some sense, maybe more interesting, at least in recent times, would be to do exactly the other thing. So someone gives you the data, all the operator correlation functions, and your task is to reconstruct the geometry of the interior. So the other direction, So this is one direction. This is like, so yeah, this is the GKPW formula for correlation. So this is like you use gravity to calculate something in CFT. But in fact, there is also exists some formalism where you take CFT data and you reconstruct the geometry. And this this direction is known as bulk reconstruction, and is an extremely interesting and active area of research. A great deal is understood, but for somebody who's interested in quantum gravity, this is of course where it's at, because a CFT is an extremely well-defined theory. Like there's some of the most solvable and most well-controlled quantum field theories that we know of. Again, there even exist now examples where those CFTs can be defined in terms of a microscopic many-body Hamiltonian, which is extremely lends itself to extremely concrete analysis. Then the question that in holography is natural is, for example, if I want to know what happens to some poor guy who falls into the black hole, how do I formulate the experience of this observer just in terms of my microscopic degrees of freedom? And actually a great deal of that sort of, a great deal has been understood in recent years. And indeed, quantum chaos is an essential ingredient in those calculations. But now quantum chaos in the precise way that you guys understand much better than me, which is in a microscopic theory, which happens to have a conformal phase. Okay, maybe that's slightly exotic, but the rest is just the kind of work that your community has been doing. And some of these results, for example, eigenstate thermalization, are extremely valuable in making statements about what happens to infalling observers, for example. Okay, yeah. Sorry? Action on what? Yeah, so S. But S is the gravitational action. Well, it is via this mapping, but of course the statement is that media CFT is a duality. Okay. And that means that you can calculate everything you want to calculate either on one side or on the other. But what I have given you here is that there is a particular class of observables, and I'm telling you the map. Like, of course, you can, in principle, always calculate function of correlation functions in a field theory. In practice, that might be a hard thing to do, but that's a procedure that is well understood. I don't know what you want to do, because one thing is that in the most general context, there is no proof of this duality. And if you wanted to prove it, one way would be to exactly calculate this and exactly calculate that, and then voila, the two are the same. Done, right? The problem is that you can neither calculate this nor this to the correct accuracy to make such a statement, at least in any non-trivial context. So now, so sorry, but this is one level. I'm trying to respond to your question. So this is one level, which would be what you really ideally want to do. You would just want to calculate both and then prove such a statement. Now that's not possible. Then what you say is perfectly correct, is that there are situations where you may be able to calculate this, but not that. Well, then you calculate this guy and use it to make inferences on this guy. There are other situations where you can calculate this, but not that. You will make the opposite inference. So for example, the question of what happens to quantum mechanically to observer who falls into a black hole, we don't really know how to calculate that in gravity, because we get into these issues where this effective field theory that I defined yesterday actually breaks down. And this CFT is a way of going beyond effective field theory. Yeah. Yes, and that's well, I was hoping to talk about that tomorrow. Of course, in the end, statements like this are a bit controversial, but there are proposed solutions, and we'll talk about them tomorrow. I think it's a good time to stop because I'm a little bit over time. I wanted to say a little bit more, but I can try and work that in tomorrow. Okay. I don't know why it's red, by the way. Does that mean that it's running out of